This video discusses the data structure called the stack, which the computer uses to implement function calls. You can also use the stacks to convert recursive algorithms into non-recursive algorithms, especially recursive algorithms that are not tail recursive. Stacks have numerous applications in computer science. After developing the tools necessary to implement a stack, I will examine some applications of a stack. A stack is a data structure in which elements are added and removed from one end only. There is an addition or deletion that occurs only at the top of the stack. Last in first out or LIFO data structure is the best explanation of how a stack works. There are two major operations happening on a stack, push and pop. With push, you can add an element onto the stack, and with pop, you can remove an element from the stack. Remember, all of these happen on the element which is at the top of the stack. For example, let's consider in a cafeteria, we have all the trays stacked up. In order to get access to the second tray in the stack of trays, you have to remove the first tray first in order to be able to access that second tray. For another example, to get to your favorite computer science book, which is underneath your math and history books, you must first remove the math and history books. After removing these two books, the computer science book becomes the top of the stack, and then it is only the time for you to access it. Same story happens to the stack of the coins. Like if you want to have access to the fifth coin from the top, you need to remove each one of the top coins one by one to access that one. Notice that the top element of every single stack is the element that actually has been added to a stack the last. And at the same time, it's going to be the first element that you can remove it from the stack if need be. That's why we call the stacks last in, first out, or LIFO. Now that you know what a stack is, let us see what kind of operations can be performed on a stack. Because new items can be added to the stack, we can perform the add operations called push. So the first step is to initialize an empty stack. As you can see over here, an empty stack does not have no elements in it. In this example, what we want to do is we want to add elements A, B, C, D, and E to the stack and see how this thing actually happens. So on the first step, we push element A or box A to the stack. So the stack now has only one member, and that member is top of the stack. Then we push box B on top of the stack. Now stack has two elements, and B is at the top. And as you can see, we can just go on and add C over there, D, and so on and so forth. In order to remove something from the stack, or let's say picking something off of the stack, you always start from the top. So in this case, when C is top of the stack, if you want to remove it, you basically are going to remove C, and then B is going to get appeared. Look at this example. So we're pushing box D on next step on top of C. And if we pop box D, then box C is becoming available to the user. Now let's talk about the stack operations. The operations available on a stack are initialize a stack, which basically initializes the stack to an empty state. IsEmptyStack is a flag that determines whether the stack is empty. If the stack is empty, it returns the value true. Otherwise, it returns the value false. IsFullStack determines whether the stack is full or not. If the stack is full, it returns the value true. Otherwise, it returns the value false. And we have push. Adds a new element to the top of the stack. The input to this operation consists of the stack and the new element. Prior to this operation, the stack must exist and must not be full. So basically, those are the two conditions that we have to check before adding anything to the stack. Then we have the top, which returns the top element of the stack. Remember, prior to this operation, the stack must exist and must not be empty. Then we have pop, which removes the top element of the stack. Prior to this operation, the stack must exist and must not be empty. Because all of the elements of a stack are the same type, you can use an array to implement a stack. The first element of a stack can be put into the first area slot, the second element of the stack in the second area slot, and so on and so on. The top of the stack is the index of the last element added to the stack. In this implementation of a stack, stack elements are stored in an array. And an array is a random access data structure, that is, you can directly access any elements of the array. However, by definition, a stack is a data structure in which elements are accessed, popped or pushed, as we just discussed about, at only one end and not randomly. That is a LIFO data structure. Thus, stack element is accessed only through the top, not through the bottom or middle or anywhere else within the stack. This feature of a stack is extremely important and must be recognized in the beginning. To keep track of top position of the array, we can simply declare another variable called stack top. We can also implement a stack as a dynamic array. In a dynamic array, you can dynamically allocate the array, which enables users to specify the size of the array. The class stack type implements the functions of the abstract class stack ADT. As you can see, the class stack type implements the functions of an abstract class stack ADT. By using a pointer, we can dynamically allocate arrays, so we will leave it for the user to specify the size of the array. That is the stack size actually. We assume that the default stack size is something like 100. Because the class stack type has a pointer member variable, which is the pointer to the array that stores the stack elements, we must overload the assignment operator and include the copy constructor and destructor. Moreover, we give a generic definition of the stack. Depending on the specific application, we can pass the stack element type when we declare the stack object. The first thing we will do is overloading the assignment operator. After we're done with that, we're going to go and come up with an initialize a stack, which is a function to initialize the stack to an empty state. The post condition for this guy is the stack top to be set to 0 because there's no element in there, right? Then we're going to need to define some checks, the booleans of is empty stack or is full stack. So the is empty stack is a function to determine whether the stack is empty or not. The post condition to it is it's going to return true if the stack is empty, otherwise returns false. Next is going to be the is a stack full, which is the function to determine whether the stack is full. Post conditions are returns true if the stack is full, otherwise returns false. Then we need to implement the push. Basically on push, we implement a function to add new item to the stack. The post condition for this thing is the stack is changed and new item is added to the top of the stack. The next logical element is going to be top, which is the function to return the top element of the stack. The precondition is the stack should exist and should not be empty. The post condition is if the stack is empty, the program terminates, otherwise the element of the stack is returned. Then we will implement pop, which is the function to remove the top element of the stack. The precondition to it is the stack exists and is not empty. The post condition is the stack is changed and the top element is removed from the stack. After that, we talk about the constructor. So the stack type constructor that is accepting in a stack size, which in this case, we kind of assume that it's going to be 100, but it can be anything. You can just put a stack size in there as a constructor and creates an array of the size of stack size to hold the stack elements. The default stack size is 100, and the post condition for this is the variable list contains the base address of the array, and the stack top equals 0, and the maximum stack size equals the stack size. So next after that, we want to do the copy constructor, which is going to be implemented. We also have 3 private members in here, which the first one is integer max stack size, which is a variable to store the maximum stack size. Next is integer stack top, which is a variable to point to the top of the stack. And then we have a pointer list, which is a pointer to the array that holds the stack elements. It is crucial to note that because C++ arrays begin with the index 0, we need to distinguish between the value of a stack top and the array position indicated by the stack top. If a stack top is 0, the stack is empty. If a stack top is non-zero, then the stack is non-empty, and the top element of the stack is given by stack top. Notice that the function copyStack is included as a private member. This is because we want to use this function only to implement the copy constructor and overload the assignment operator. To copy a stack into another stack, the program can use the assignment operator. So generally speaking, let's just do a quick review over here. If the stack top is non-zero and the stack is non-empty, the top element is given by stack top minus 1. So don't let the start from 0 according to the array standards confuse you over here. Here in this slide, you can see the data structure that we just discussed. So in this slide, the stack is an object of type stack type. Note that the stack top can range from 0 to max size. If a stack top is non-zero, then stack top minus 1 is the index of the stack top element of the stack. Suppose that maximum stack size is 100. Note that the pointer list contains the base address of the array, which actually holds the stack elements. That is the address of the first array component. Next, we will talk about how to implement the member functions of the class stack type. But before going there, let's talk about initializing the stack, okay? So let us consider initialize a stack operation. Because the value of a stack top indicates whether the stack is empty or not, we can simply set the stack top to 0 to initialize the stack, as you can see in this slide. Okay, next is to check if the stack is empty or full, and this happens through 2 very simple functions. So we discussed before that the stack is empty if the stack top equals 0, which means the pointer is right at the bottom. And in that case, the only thing we need to check is we check if the stack top is 0 or not. If this expression turns to be true and we return it, then the isEmpty stack is going to be true. If this expression is not 0, it returns false, and it shows isEmpty stack is false, meaning the stack has some elements in it. For checking if the stack is full, the condition is if the stack top equals the maximum stack size. In that case, the only thing we need to check is if we can check if the stack top is equal to maximum stack size, and as you can see, this expression is true when your stack is full. So it returns, and its full stack is going to be true. Now let's talk about push. So push is to store a new item in the array component indicated by stack top. So wherever stack top is pointing to, we want to put the element right over there. Of course, the next logical step is going to be to increment the stack top so that now it points to the top of the stack again. Remember, overflow can occur if we try to add a new item to a full stack. So if the stack maximum size is reached and we add another item, the stack overflow actually happens at that point. Let's take a look here. So assume that we already have a stack of size 100, maximum size 100. which the top of the stack is at 0.4, and we already have SUNN in the stack. Okay, so the goal here is to add a Y to the end of it, so we have the word sunny in the stack. At this point, what we're going to need to do is basically add Y to position 4 and move the stack type to 5. So let me go back one slide. So as you can see right here, the stack type is at 4, right? And we have all the way up to here. And what we do is we add Y at the position 4 of the stack, and the stack type is now at 5, ready for the next item to be added. So the respective code for doing so is going to be, as you can just see right now. So the first thing is we check to make sure if the stack is full or not. If it is not full, then we simply go for the stack type item of the array and set it to be the new item. Remember, the stack type is always showing the top of the stack, which has no element in there. So we add the new item over there, and we increment the stack top by 1 to show the top of the stack again, and hold on over there. So now that we discussed how the push works, it's time to talk about how to return a stack element, which is always at the top. So to do so, again, as you can see, we check if the stack is empty or not, true and assert. And if a stack is not empty, then we want to return the array item, which is at the stack top -1. Let me just go back to that slide and remind you that at any case, what the stack top is showing is above the last element. So if we want to return this Y, we basically need to reduce the stack top by 1, so it shows the array element of 4, and then move from there. So now that we discussed this, let's go ahead and talk a little bit about the pop, which basically removes the top element of the stack. So pop is used to remove an element from the stack and decrement the stack top by 1, which is the logical next step or post condition of a pop. What we do is first we check if the stack is empty or not. Remember, we do this check almost in every single operation that we do on a stack, and we simply do in a stack top minus minus. And that's pretty much it. That's all we need to do. When we point down, that element is out of the stack. Like in this example, if we are at 0.4, in order to get rid of D, the only thing we need to do is we need to reduce the stack top by 1, turn it to 3, pointing here, and the D is going to be out of the game. And as you can see, this is what happens. The stack top is 3 now, and that is done. Next, let's talk about copy stack. The function copy stack makes a copy of a stack. The stack to be copied is passed as a parameter to the function copy stack. We will, in fact, use this function to implement the copy constructor and overload the assignment operator. The definition of this function is, as you can see right now in the slide, and it's as simple as creating a new array, setting the stack type as the stack type on one array, loop through it, read the items one by one from the original, or let's say the source array, and when we read every item of the source array, we assign it to the item in the new array that we just created, and we move from there. Finally, at the end, the stack top is going to be the same as the stack type of the original, and the maximum stack size is going to be the same. We also will define a constructor and destructor for the stack. So these functions are to implement the constructor and destructor are pretty straightforward. The constructor with parameters sets the stack size to the size specified by the user. Remember, we decided to do a dynamic array, so user can basically decide what size it's going to be, and it's going to set the stack top to 0 at the beginning because there is no item, and creates an appropriate array in which to store stack elements. If the user does not specify the size of the array, in which to store the stack elements. The constructor uses the default value, which in our example in this video we decided it could be 100, to create the array of size 100. Then the destructor simply deallocates the memory occupied by the array, that is the stack, and sets the stack top back to 0. Let's take a look at the definition of it. Okay, as you can see over here, we have the constructor, and then we have the destructor over here that basically takes care of the implementation of what we just explained. Remember that we have a maximum size of 100 set to be our default value, unless user actually gives us the size, and we go from there. Regarding the destructor, as you can see, we simply delete the array list, which deallocates the memory occupied by that array. So next in line is the copy constructor. The copy constructor is called when a stack object is passed as a value parameter to a function. It copies the values of member variables of the actual parameter into the corresponding member variable of the formal parameters, which, as you can see, it simply gets implemented by passing the other stack to the copy stack, and that's it. We just copy it. Now that we took care of this, let's go ahead and see how we are overloading the stack assignment operator. You should remember from the classes that any class with pointer member variable, the assignment operator of that class must be explicitly overloaded. The definition of function to overload the assignment operator for the class stack type is as you can see over here, which is actually very simple. So what we need to do is we need to check and avoid any type of self-copy, and if that's not a self-copy, the other stack is going to be passed to the copy stack, and a pointer to that is going to be returned. Now that you know how to implement the stack operations, you can put the definitions of the class and the functions to implement the stack operations together to create the stack header file. For the sake of completeness, we next describe the header file. To save space, only the definition of the class is shown on the video. No documentation is provided. Suppose that the name of the header file contains a definition of class stack type is mystack.h. In this case, the header file for mystack.h looks like this. So let's quickly review what we have put in there. So the template class type is defining the class stack type, which is inherited publicly and from the stack ADT. Public members are constant operator overloading. Then we have the initialize stack. Then we have is empty stack, is full stack. We have push, top, and pop. And we have the stack type integer stack size initiation, which starts with the size 100. And then we have the stack copy constructor, and then we have this stack destructor. Pretty simple. We have this three maximum stack size, stack top, and the pointer list over there as a private member. And this is nothing but what we just reviewed in this video from the get-go. I just aggregated and put them together in a header file for the ease of readability. Because an array size is fixed, in the array or linear representation of a stack, only a fixed number of elements can be pushed onto the stack. If in a program the number of elements to be pushed exceeds the size of the array, the program may terminate in an error. We must overcome these problems. We have seen that by using a pointer variable, we can dynamically allocate and deallocate memory. And by using linked lists, we can dynamically organize data such as an ordered list or unordered list. Next, we will use these concepts to implement a stack dynamically. Recall that in the linear representation of a stack, the value of a stack top indicates the number of elements in the stack. and the value of a stack top minus 1 points to the top item in the stack. With the help of a stack top, we can do several things. Find the top element, check whether the stack is empty, and so on. Similar to the linear representation, in a linked representation, stack top is used to locate the top element in the stack. However, there is a slight difference. In the former case, stack top gives the index of the array, and in the latter case, stack top gives the address or memory location of the top element of the stack. When we use linked list to define a stack, we have a default constructor as you can see on this slide. The default constructor initializes the stack to an empty state when a stack object is declared. Basically what it does is setting stack top to null pointer as you can see over here. As we discussed before, we need to check if the stack is empty or full. We did this by using the arrays in the past. When using a linked list, function isFullStack does not apply. Logically, the stack is never full. And in the same way, stack is empty if the stack top is null pointer. Next is initialize a stack, which basically reinitializes a stack on an empty state. So this must deallocate memory occupied by current element and then set the stack top to null pointer. So for the push, what we need to do is we need to find the stack top location and basically add a new link. Let's look at how this happens. So what happens is we use creation of a new node at the beginning. So we create a new node, and then the stack type, which used to point over here to the top element of the stack, now needs to get pointed up there. To do so, what we do is first we make sure this new node that is just created is pointing to the next element, as you can see over here. Remember, in the linked list, we don't want to lose the list through losing the links, and that's why before we even move the stack top, we make sure the element that we recently added is pointing to the last element, which used to be the stack top element. When we're done with that, basically what we do is we make sure now a stack top is pointing to that element, and then the new node link is also pointing to that element, which basically at this point we have added a new node to the linked list, or speaking of a stack language, we have pushed one on top of it. So regarding return the top element, as we discussed before, in this case the only thing we need to do is to check if the stack is empty first through an assert, and if a stack is not empty, we basically need to return whatever information stack top pointer is pointing to. Pretty straightforward in comparison with what we did in the arrays. So what about the pop? For popping, the only thing we need to do is we need to make sure this pointer, which is pointing to this element, will be pointing to element B, and with that, C is going to be popped out. Let's see how it works. So what we do is we create a temporary pointer to point to the stack top. Then we move the stack top, making sure it's going to point to the next element, not the element we want to pop. At that point, we delete whatever information this pointer is pointing to, which is going to end up having that element completely popped out of the stack. Next to discuss is copy a stack. So the copy a stack function makes an identical copy of the stack, which has the similar definition to copy list for the linked list. Since we discussed it before in very fine details, we're not going to go through it again over here. I refer you back to the linked list copy constructor if you don't remember how it actually works. Constructors and destructors of a stack while being implemented through a linked list are actually exactly similar to those for the linked list itself. So we do the exact same things. The only extra thing that you need to do here is to set the stack top to point to the last element added to the stack. Next to do is overloading the assignment operator, which basically happens with passing whatever you want to assign to a new stack through the copy stack. If you remember when we talked about the linked list, we talked about the copy list. And this is exactly the same thing. The copy stack is the same as copy list. And in this case, when you want to assign other stack to this stack, you simply pass it to the copy stack to be copied over, and that takes care of the job. If we compare the push notification of the stack with the insert first function discussed for general lists and the video we had about the linked list, we see that the algorithms to implement those operations are similar. A comparison of other functions such as initialize stack and initialize list, is empty list and is empty stack, and so on, suggests that the class linked stack type basically can be derived from the class linked list type. Moreover, the function pop and is full stack can be implemented as in previous videos. Note that the class linked list type is an abstract and does not implement all of the operations. However, the class unordered linked list type is derived from the class linked list type and provides the definitions of the abstract functions of the class linked list type. Therefore, we can derive the class linked stack type from the class unordered linked list type, and then we can define the class linked list type that is derived from the class unordered linked list. The definition of different functions are very, very similar to what we did before in the linked list type. Okay, now that we talked about and covered a couple of methods of how to implement a stack, it's time to talk about the application of stacks. So let's go and see how stacks are going to help us with calculation and operations in computer science. The usual notation for writing arithmetic expressions, which is the notation that we learned in elementary school, is called infix notation, in which the operator is written between the operands. For example, we have A plus B, and the operator plus is between operands A and B. In the infix notation, the operators have precedence. That is, we must evaluate expressions from left to right, and multiplication and division have higher precedence than do addition and subtraction. If we want to evaluate the expression in a different order, we must then include parentheses. For example, in the expression like A plus B times C, we first evaluate the multiplication between B and C, and then we add the result to A. With that preface, let's talk about history a little bit. In the early 1920s, the Polish mathematician John L. discovered that if operators were written before the operands, which is called prefix or Polish notation, for example, plus AB, the parenthesis could be omitted. So if you write them like this, no parenthesis is actually needed anymore. Continuing on that, in late 1950s, the Australian philosopher and early computer scientist Charles L. Hamblin proposed a scheme in which the operators follow the operands, which is called postfix operators, resulting in the reverse Polish notation. This has had a huge advantage that the operators appear in the order required for computation. Let's take a look at some examples. So when you have A plus B in infix expression, the equivalent postfix is AB plus. So the order, as you can see, we have the order. If you have a plus b times c, you can do it a, b, c times plus. As you can see in this order, that multiplication is connected to b and c, and then the result of all that is going to get summed with a. Another example is this guy. So you see a times b plus c is being written this way. So we put the operands first, then the operation that's supposed to happen over them, and then the next operand with the next operation. So in this case, as you can see, first a and b are going to get multiplied, and then the result is going to get added with c. So using parentheses, see how the parentheses are being omitted. So if you have a plus b times c, you can simply put it ab plus. So the plus is going to happen here first because we're reading from left, and then the result is going to get multiplied by c. Again, another example is a minus b and the result multiplied by c plus d. As you can see, we can write it like this, ab and a minus, so we move here. A is being given, b is being given, minus, so we do the calculation over there first. Then we have CD with plus. Okay, we do the calculation. And then multiplication comes. That means the result of these two, and so on and so forth. So looking at this column, comparing it with this column, you can see how parentheses could be omitted if we use the postfix expressions. Shortly after Lukasiewicz's discovery, it was realized that postfix notations had important application in computer science. In fact, many compilers now first translate arithmetic expressions into some form of postfix notation and then translate this postfix expression into machine code. Postfix notations can be evaluated using a very simple algorithm. So first, scan the expression from left to right. Then when an operator is found, back up to get the required number of operands, and then perform the operation and continue. Let us evaluate an expression, for example. So let's look at the expression 63 plus 2 times equals. Let us evaluate this expression using a stack and the algorithm that we just talked about. Looking at the slide, you can see how this expression gets evaluated. Read the first symbol, 6, which is a number, then push the number onto the stack. We are here, the number is pushed into the stack, okay? Then push the number onto the stack, second number, 3, is getting pushed onto the stack. The next thing is compiler arrives at plus. When compiler arrives at plus, what happens is going to pop these two out of a stack and add them. Remember, the pop happens twice because compiler already knows the operator plus needs 2 operands. So 6 and 3 gets popped out, then they're going to be summed up, and the number 9, which is the result, is going to be pushed back to the stack. Okay? And then when this job is done, compiler goes back here, and now is the time to read 2, which, because it's an operator, we simply push it to the stack. As you can see here, now we have 9 and 2 pushed on top of it. Next to be read is the multiplication. So multiplication is an operator that needs 2 operands. So compiler goes back to the stack and pops twice to get 2 operands for this operator. 9 and 2 come out. The multiplication happens, and the result, which is 18, gets pushed back to the stack again. Okay? And when this happens, we go back here and continue reading. We arrive at equal. So equal means end of operation, which in that case, compiler is going to go ahead and pop back whatever is in the stack, which in this case is 18, for the result. Pretty neat. So let's quickly go through again. So we start from the left. We'll read the operators. When we see, the operands. When we see the operands, we just push them to the stack. When we see an operator, we check how many operands are needed for that operator. We pop back as many times as needed, like twice for plus. do the calculation, and the result is going to be pushed back again, and so on and so forth. We move on over whatever expression we have to get to the end of it and have the final result, which happens when the equal sign is being reached to. And with equal sign, we only pop back once, and the result is going to be out. Remember, symbols can be anything, numbers or anything else. Plus, minus, multiplication, and division are operators, require two operands. Therefore, the stack is being popped twice and evaluate the expression happens. If a stack has less than two elements, in these cases, we're going to receive an error. So if the symbol is equal, expression ends. So we pop and print the answer from the stack. If a stack has more than one element at this point, an error happens because it looks like an operation has not happened that's supposed to happen. When we arrive at equal sign, we only must have one element in the stack. So if symbol is anything else, expression contains an illegal error, which means we cannot do that arithmetic operation. Let's assume the postfix expressions are in this form: #6, #3 plus #2 times equals. If symbol is scanned as pound, next input is a number. If the symbol is scanned as not pound, then it is an operator, may be illegal, or an equal sign end of expression. Assume expressions contain only plus, minus, multiplication, and divisions. Now let's review the main algorithm. So we start with reading the first character, and then while not the end of input data, so basically a loop that checks that there is still some data, we initialize a stack, we process the expression, we do output the result, and then we go on and get the next expression. To simplify the complexity of the main algorithm we just discussed, we can break it down to four smaller functions: evaluate expression, evaluate operator, discard expression, and print result, which every single one is going to take care of one step of the main algorithm. The function evaluate expression, if possible, evaluates each postfix expression. Each expression ends with symbol equal sign is actually what is going to trigger this evaluate expression. The next function is evaluate operator, which this function evaluates an expression, needs two operands saved in the stack. If less than two, returns an error, and also checks for illegal operations. Next function, discard expression, is called when an error is discovered in the expression and therefore reads and writes input data until it gets to equal sign. Next function is print the result. The function print result, if the postfix expression contains no errors, which means the calculations have happened properly and free from any mistake or error, it prints the result. Otherwise, it outputs an appropriate message, which result of the expression is in the stack and output is sent to a file. So let's quickly go back to the main again and review main quickly together. So as you can see, initialize the stack, process the expression, output the result, and get the next expression. With that review, we conclude our video on the stacks in C++.